of the workshop. It's a great pleasure to introduce Alastair Rucklidge, who's going to take us back to the world of algebra and back into some kind of physical reality with three-wave interactions.
So thanks very much for the invitation to speak here. And since this is the last of the scientific contributions at this workshop, I'd like to take this opportunity to thank the organizers, Peter and David, for putting on such an interesting workshop for us this week. Part of the point was to bring together mathematicians and physicists interested in liquid crystals and related problems and get them to talk to each other. And from my point of view, this has worked extremely well. I've learned a huge amount this week. So thanks to the organizers, and thanks also to the speakers who have clearly put in such an effort to reach out and communicate with people from different communities. So this is work that is joint with Anne Skeld and Mary Silber on the Faraday wave problem, and Edgar Knobloch, Andrew Archer, and Peter Olmsted on the soft matter quasicrystal problem. Two of these people are here today. So just to remind you what a quasicrystal is, this is taken from the original paper of Sheckman in 1984. So this is a crystal-like object, a solid, that has orientational order but not translational. So in its X-ray diffraction spectrum, it has 10 peaks here, and we know we can't fill space with dodecagons, and so, or the appropriate object here. So these things can't be periodic. But what is perhaps less well known in this community is that similar kinds of objects appear in a wide variety of other places. This is an example from a fluid mechanics experiment called the Faraday wave experiment. Faraday waves, you take a tray of oil or liquid, sort of this kind of size, and you shake it up and down with an acceleration usually 3 or 4 or 5 times gravity, peak acceleration. This experiment has 2 different frequencies components in the forcing, and you end up with a pattern of standing waves on the surface of the liquid, which has, in different contexts, can be squares or stripes or hexagons, but under suitable conditions forms these quasi-patterns. So they're distinct from quasicrystals because they are not, it's a liquid, so it's not a crystal, but it still has this quasi-periodicity feature, which you can see in the image here of the surface of the experiment. And this image here is the Fourier transform of the surface image, and you can see, in this case, 12 peaks arranged in a circle, and there's a second circle with an additional 12 peaks arranged. One of the things I'm going to be talking about is the importance of having 2 circles when you think about stability of these quasi-patterns. So this has a 12-fold symmetry. So they show up in Faraday waves. They show up in nonlinear optics with this is a laser with optical feedback. Again, 12 peaks in a circle. And they show up in soft matter problems. So this is an image of a block copolymer system. So this block copolymers are, for those who haven't met them before, are polymers made up of different units. So you have, say, one type of unit, and you've got a whole bunch of those units in a row, and then it's attached to a string of some different component. And possibly there could be 2 different components, or 3, or they can be arranged in one after the other, or they can be arranged in more complex architectures. So this is the image of the system, and here's the Fourier transform that shows up again. We've got 12 peaks in that circle. So I know that soft matter is not the same as liquid crystals, but I'm hoping that there's enough common interest between the materials that go into making liquid crystals and the materials that go into making some of these soft matter quasicrystals that I hope they will be of interest to you anyway. So what I'm going to talk about today, well, I'm not going to talk about this first one about existence. Pascal mentioned that issue yesterday. I'm going to talk about stability. So what does it take to make a quasi-pattern stable? And I'll do that in the context of the Faraday wave problem, and emphasize the role of three-wave interactions in making a quasi-pattern stable. Three-wave interactions can do other things as well. They can produce spatiotemporal chaos in the Faraday wave experiment, and I'll discuss that a little bit, and then I'll try to bring those two ideas into the soft matter context. And since this is a new area for me, I've worked on Faraday wave problems for some time now, but not on these soft matter problems. So the ideas are at the formative stage. We're just working out how to do this, and so I'd be very grateful for comments and feedback. So two length scales. So here's another example, not the Faraday wave problem. This is an example from Turing instability. So a Turing pattern formation is perhaps one of the most fundamental examples of pattern formation where you, and it comes in reaction diffusion problems. In this example, there's two reaction diffusion layers going on. There's a top layer and a bottom layer, and they're coupled through some membrane. And the length scale of the pattern are different in these two layers, and the coupling means that you have a problem here with two length scales, and you get these complex, spatiotemporally complicated patterns here, and with two length scales showing up in that image there. And also to show you some examples in the soft matter context that have two length scales, it's perhaps most obvious here in this middle one. You've got the sort of fine lengths going on in the middle of these stripes here, and then there's a broader length scale with the larger length scale with these sort of thick gray stripes. Here, I will come back to this one here later on. I'll show you the Fourier transform of this image later on. And here is a quasi-crystal example in a block copolymer. It's been decorated with a Penrose-like tiling, but its Fourier transform is what I want to draw your attention to, and there are two circles here. So there's some evidence of two length scales showing up in all of these examples. So I showed you some from the Faraday waves. I showed you some from Turing patterns, and here is a two length scale showing up in these soft matter quasicrystals. So in the Faraday wave problem, the three-wave interactions, what that means is we've got here two length scales are being excited. So the flat surface is always a possible state of the Faraday wave problem. You drive it with this two-frequency forcing, and if you drive it hard enough, you get patterns forming on the surface, and it's arranged so that two different well, the way to think about it is that in principle there are two different wavelengths that are being excited. So in two dimensions, this corresponds to two circles in Fourier space, and they are, if you take a vector here on, say, the inner circle here, it's composed of the sum of two vectors on the outer circle. That means that if each of these vectors represents a wave, and if you have nonlinear interactions between two waves, if you got e to the I, say, k1 dot x times e to the I k2 dot x, the nonlinear interaction between those will give you e to the I k1 plus k2 dot x, which is this middle vector here. And so there's nonlinear interaction between these two waves on the outer circle with that wave there on the inner circle. So that is clearly going to be a feature of this system here. And here, so that was a quasi-crystal example. Here is a spatiotemporal chaos example. These are 4 different time snapshots where it's evolving in this irregular fashion. And here are the Fourier transform of one of those images showing, actually, in this case, 3 length scales are playing a role. So how do we think of that in a pattern formation context? Well, here I've drawn a graph of the growth rate as a function of wave number, and most waves are damped. Most wave numbers are damped, have negative growth rate, but we've got two bands here centered around wave number 1 and centered around wave number q, where q is some number less than 1, where they waves will grow, and the growth rates will be, for wave numbers 1, I'm going to call that growth rate mu, and for wave numbers q, I'm going to call the growth rate nu. So at the linear level, you represent the amplitude of your pattern as sums of waves, e to the I k dot x and e to the I q dot x, where k are going to be vectors with length 1, and these q's, sorry, this should be a q here, are going to be vectors of length q here, which is that thing there. And the amplitudes of the k vectors will be z, and the amplitudes of the q vectors will be w. And so we know now at the linear level how z and w will grow. So if we start here with, say, one vector, we're going to take k1 to be the vector 1, 0, and q1 to be the vector q0, then and this vector k1 has amplitude z1, the vector q1 has amplitude w1, and they're complex conjugates, of course. Then the time evolution of z1 at the linear level will be z1 dot is mu z1, and w1 dot is nu w1. So those will be the starting point. And we can now ask, well, what about three-wave interactions? What three-wave interactions are there? So z1 will be, this vector here, k1, can be written as the sum of this one here, which is length 1, and this one here, which has also got length 1. This is an equilateral triangle. And so if I call this vector z, it's conventional to label them z1, z2, z3. So this one here is z3 bar, this one is z2 bar, and so it's going to be the product of z3 bar and z2 bar that will influence z1. So we've got a z2 bar, z3 bar quadratic term that comes into the equation for z1. And similarly, if we have, here's w1, w2, w3, so w3 bar times w2 bar will enter into the equation for w1. So these are the standard interactions that would give you hexagons as your basic pattern. They don't involve both circles. So the next stage, we think about what waves will come from both circles. So it's easier to start with the w1 first. So w1 here, this vector here, q1, is the sum of these two vectors here, z. So this will be z6, so that will be k6 and k7. So we've got k6 plus k7 is equal to q1, and that means we'll get a z6, z7 term in the equation for w1. And if we take this triangle and rearrange it, we have here a vector here for z4, and then another one, a short one. So it's a long vector z4 and a short one here that is w4, give you zk1, and the other way around as well. So we'll get two terms coming into the z equation, z4 w4 and z5 w5. That's one three-wave interaction. But the other one, so that's 2 on the outer circle and 1 on the inner circle, but you can do it the other way around, of course, provided this inner radius ratio is bigger than a half. So you get 2 on the inner circle, so this is, say, Q6 and Q7, and they add up to K1, so we get a W6, W7 term in the Z equation. And if you take that triangle and rearrange it, you get a long one and a short one adding up to Q1, so that is K8 and Q8 adding up to Q1, and K9 and Q9 adding up to K1. So you get a W8, Z8 and W9, Z9 term showing up in the W equation. Okay, and that, putting it all together, here is Z1, so with vector K1, and it's going to be influenced by three-wave interactions by all of these other vectors here. So just putting together all the vectors I've drawn. And this vector here, Q1, will be influenced by all these other vectors here. So there are 8 other vectors, and there are 8 other vectors here, different 8. So, so that's putting the amplitude equations up to quadratic order together. So what has this told us? Well, it's told us there's a lot going on. And if you now say, well, hang on, that was just K1 and Q1, right? So if you imagine that, so all of these vectors, these waves, in principle, could influence this one. And then you need to say, well, okay, what about that one, and that one, and that one, and that one? Well, you have to take a copy of this and rotate it appropriately. And all of these waves will influence that one. Well, how about that one, and that one, and that one, and that one, and that one? And then so you take a copy of this and rotate it appropriately and add it on top. And once you start doing that, you get a lot of vectors. So what this is saying is as soon as you've got 2 wave numbers in your problem, and they're within a ratio of 2 of each other, you really should be thinking of interaction of all your vectors on these 2 circles. You get a finite set for one special value of the radius ratio. Okay, you get a dense set for every radius ratio apart from 1. If you ignore quadratic interactions between modes on the same circle, so if you ignore these 60-degree interactions, there are 2 special radius ratios. If you keep those 60-degree interactions, then the only closed set of vectors corresponds to 12-fold quasi-pattern. If you drop the 60-degree vectors as well, interactions, you get a 10-fold quasi-pattern as well. So this seems to distinguish 12-fold quasi-patterns from all others in problems that have 2 wavelengths in them. This is you can get quasi-patterns in problems with only 1 wavelength, in which case it's a different story. But if it is 2 wavelengths that are coming in and influencing how your quasi-pattern forms, then there's going to be something special about 12-fold quasi-patterns that are distinct from 10 and 8 and 14 and 16 and 18 or all the other possibilities. So I pose it here as a question. I've done this by trying all combinations up to thousands and thousands until I've convinced myself that this is true for all regularly spaced combinations of vectors. I don't have a formal proof for this, and there's a sort of an analogous problem in 3 dimensions, which I'll just sort of leave there as a question.
But there must be something robust about this, though, because if it was so special, you wouldn't see it.
So special? Well,
I mean, surely in any physical problem, you're not going to hit this particular.
Exactly. That's okay.
So there's something special and robust about this.
Yes. Okay. So you can ask the question. So if I can see if I understand your question. Supposing you have a physical problem which does not have this exact ratio. This number is 0.5160, right? So what if you're not exactly there? Well, it's robust to small changes. So what that means is your physical problem might not end up with its vectors lying exactly on the circle's that are given to you by linear theory. So, and that's quite common in these pattern forming problems, is the linear wavelength is not the wavelength you see in your nonlinear solution. Just it's close, but it's not exactly the same. So if you're not exactly at this number, you might still expect to see this. The other thing is that maybe this is a wrong impression, but certainly So my impression is that people who are doing experiments will tune their knobs and play with the parameters and try different frequencies and depths of fluid and so on. And wow, it's a quasi-pattern. Let's write a paper about that. Okay, so that what we're seeing is perhaps a little bit selective. They also show quite, spatiotemporal chaos where there are other wavelength ratios that are apparent. We see the quasi-patterns because they're interesting and people show them to us, I think.
The spirit of robustness in the case where it bends, what is the measure that characterizes the distribution of the vectors that appear? Is it uniform?
Uniform, yes.
Oh, so this is not robust.
Yes, well, let me show you some numerical examples where it looks. Okay, so so we've got this fairly complicated system of modes all interacting with each other. Is there anything that we can say about it? And at one level, there is. What I'm going to do is pull out of this mess, say just this one here. Okay, just one Z, another Z, and one W. Okay, so just look at the interaction of those three and see what happens in that case. So if you do that and write down the evolution equations, so because there's only those two Z's, we don't have the Z2 bar, Z3 bar terms. All the hexagonal things have gone. We're just pulling out this single combination of quadratic terms to focus on, and then I put in some sort of typical cubic terms. These are the kinds of things that you'd get if you were doing this for the Swift-Herrenberg equation, for example. And the outcome of what these, so we've got three complex amplitudes, and what they do depends crucially on these quadratic coefficients, and in particular whether they're of the same sign or of the opposite sign. If they're the product of those two coefficients is positive, so they're the same sign, then typically what you see out of these three equations is stable, steady stripes. That means either Z1 is non-zero and the other two are 0, or Z2 is non-zero and the other two is 0, or W1 is non-zero and the other two is 0, or stable ROMs. ROMs are when you have an equal mixture of Z1 and Z2, and then W1 is also non-zero. So that's the case when these quadratic coefficients are the same sign. If they're of opposite sign, then you can get these possibilities as well, but you can also have the possibility of time dependence. There's Hopf bifurcations, there's chaos, there's heteroclinic cycles, there's all kinds of good things. This is just one of those many mode interactions, and so the same conclusion would apply to any of the many combinations of mode interactions that we've seen. So just to show you a picture of what you get, so this is a typical example when these quadratic coefficients are of the same sign. Red means Z stripes, that means Z1 is non-zero, the other two are 0. The cyan is W stripes, and the blue is stable ROMs. And this is where you have both of them, where the product of these quadratic coefficients is negative, Z stripes, W stripes, stable ROMs, and then there's this white region here where you get the time dependence and other things as well. So what can we say about the problem with all these mode interactions put together? Just based on this, what might we expect to see is, well, the quadratic coefficients are, the signs of these quadratic coefficients, whether the same or opposite, is going to be important. We had two directions, if you remember, two types of mode interactions. We have this one and this one. Oops. Sorry, that's not right. We've got this one, too long and a short, or too short and a long are the two types. And so we've actually got two pairs of quadratic coefficients to worry about. If both pairs are of the same sign, then we might expect to see patterns where the amplitudes are all reinforcing each other. That's where we might expect to see stable quasi-patterns. If they are both of opposite sign, we might expect to see more complicated time dependence where the amplitudes are going to go up and down in magnitude. They're going to come and go. And so this is where we might expect to see spatiotemporal chaos. For this special value of this radius ratio, that is where we're going to see the quasi-patterns for that special value. So just to illustrate this, what Anne Skelton and Mary Silver and I have done is take some experimental work. This is the same quasi-pattern image that I showed you. Here is now a bit more detail. There are two parameters here. It's the amplitude of the two frequency components, and this is where the quasi-patterns are found as a function of those two amplitudes. And this is measured in units of gravity. So this is 6 times gravity, 4 times gravity. There's in fact a third frequency brought in, so 3-frequency forcing here. And we have computed these quadratic coefficients from the Navier-Stokes equations using a technique that Anne developed, and tried to overlay it on the experimental results. So this is the as the experimentalists vary the relative phases of the 5 and the 2 components of the forcing, what you get varies. So they've picked a value in here in the middle of this quasi-pattern region, and they found that as you varied phi 5 and phi 2, you sometimes got quasi-patterns, sometimes got spatiotemporal chaos. Here, white is where they're getting, so they're measuring here the 30-degree angular autocorrelation function. So white is quasi-pattern and black is spatiotemporal chaos. We've computed the product of the relevant quadratic coefficients, and now here I've overlaid them on this diagram, and you can see if you focus on the red one here, you get the spatiotemporal chaos in regions where, at least roughly, the regions of spatiotemporal chaos seem to lie roughly where these quadratic coefficients actually it's where they vanish. This red line here is where they're 0. Otherwise, they're positive. So there seems to be some hope that not only are these ideas relevant to what this experiment is doing, but there's also hope of making some quantitative comparison between these theoretical ideas and something real. Being I'm not an experimentalist, and I'd like to have my hands on something that I can actually look at. We wrote down a Swift-Hohenberg-like PDE where all these things can be controlled and can be run on a computer. It's got a linear operator which is like the Swift-Hohenberg one, except it's got 2 wavelengths in it, and it's got some nonlinear terms, u squared, u Laplacian u, grad u squared, and a cubic term. So just as a function of the parameters, the growth rate of the Z modes, the growth rate of the W modes, the red here is where we're getting the stable quasi-patterns, and that is for this special radius ratio. It's 0.5176 is the case where all the quadratic coefficients are of the same sign. And to show you an example, this is a quasi-pattern solution, stable quasi-pattern solution of that PDE, and there's its Fourier spectrum. And I've drawn in cyan and magenta the two two critical radii in this problem here. So if we now change it so that these quadratic coefficients have opposite sign, in cyan here is the region of spatiotemporal chaos, and here's an example. So it's a continuously evolving complex pattern here. Its Fourier transform appears to be uniformly dense on 2 circles, to the extent that it's a periodic box, so up to that point. And this is a time trace of the amplitudes on these 2 circles, and they just go up and down, and they just keep on going. And there's a wide variety of other things that happen as well. So just to conclude this first part, we've got in these 2-wave problems, if the ratio between the 2 wavelengths is between 1/2 and 2, then we should think of 3-wave interactions in both directions. Once you do that, then you've got this infinite number of waves on these 2 circles, with the exception of this special value that's associated with 12-fold quasi-patterns. And it may be that it's no coincidence that 12-fold quasi-patterns are the most commonly found one, and maybe for problems with 2 waves, the reason could be something to do with this. What you might see, though, will depend very much on these quadratic coefficients, and I've shown you that they can be computed for real physical problems, Navier-Stokes equations in this case. And quasi-patterns are, or at least time dependence is most likely in the case where they have opposite sign. So now on to the second part, which is to try and relate this to soft matter problems. And this is where I'm on in new territory, on thin ice, as it were. So if I make a mistake, please do correct me. So the idea here is we're looking at a block copolymer. So in this cartoon here, blue represents one element, chemical element that's been polymerized to make this blue chain, and red is a different chemical element. And you might imagine that, say, blue is soluble in water and red is insoluble. So if you mix this up in water, then the blue bits will point out and the red bits will come together, and you can get a variety of different configurations like membranes, cylinders, or micelles, which are spheres, where all the red bits are in the middle and the blue bits are on the outside. So what's been observed in the past few years is that colloids, which are suspensions of these micelles, can self-assemble into a variety of crystalline and quasi-crystalline structures. So this has been around for maybe 7 or 8 years, and the idea that having two length scales might be responsible for stabilizing them was proposed by a couple of people in 2007, a couple of groups in 2007. But as far as I know, the connection between this idea and quantitative predictions for polymers hasn't really been made quantitative. So, and it's not surprising, it's quite difficult. So what I propose to do is outline how we plan to go down this route, and this is where I'd be very pleased to have comments. So the idea is, So the idea is to use density functional theory and phase field crystals, and to make the connection between the polymer physics, or the interactions between micelles, and the pattern formation ideas that I talked about in the first part. So we have, if we imagine we've got a suspension of these micelles and they interact through some pair potential, rho of x here is going to be the density of the micelles. There's a pair potential between two separated by a distance x minus x prime. So this is the energy of interaction, and then there's the sort of the entropy term over here. We've seen similar equations many times this week. And the task is to minimize this free energy subject to a fixed number of particles in the system. That's a variational problem, or sorry, a minimization problem. There's also a time-dependent version of this, which is written in this form. You've got a functional derivative of this free energy with respect to density, and then there's a particle mobility here, capital M. So the idea is that we've got you start with a fluid where this density is uniform, and you lower the temperature, and there's a transition to F being minimized by different crystalline or quasi-crystalline density distributions. So just as a sort of a starting point, Andrew Archer has put in a potential with two length scales in it, just to see if we can make quasi-crystals out of a problem with two length scales. So this is a graph of his potential. It's flat on the top, which means it's a clustering type potential. I think we saw an example of that earlier this week. And it's got this shoulder here in the middle. So it doesn't have two minima that you might imagine, some Leonard Jones type, higher version of Leonard Jones with two minima. It just has a shoulder, and that appears to be sufficient to get a quasi-crystalline arrangement of particles of density here. This is starting with random initial conditions. that's the starting point. The next idea is to transform this into a phase field crystal, and that involves taking the free energy and migrating it somehow in a way that I must admit I'm not completely sure I understand fully, into a 2-point correlation function here. So this looks similar to what we had before, but instead of an interaction potential, we have a 2-point correlation function. And we've got, instead of the density, it's the density difference with respect to the liquid reference state. And higher order terms. So there'll be a 3-point, 4-point, and so on correlation function as well. Okay. The idea then is to say, well, if you've got one length scale, the 2-point correlation function will be peaked at some length, at that length, and in Fourier space, it will be peaked at 2 pi divided by that length. You expand around that peak, so you get so it's a peak in Fourier space. You've got a non-zero peak in Fourier space, so you have to go to a quadratic function, but it's going to be a quadratic function of k squared to make everything make sense. And then you transform back into physical space, and where you have constant k squared k to the fourth, you end up with a constant Laplacian and Laplacian squared term times a delta function. And that then, when you do all the integrals and do the minimization, you end up with something here that looks like the negative Laplacian of the Swift-Herrenberg equation. And this is plus another term. And this is where the connection with pattern formation lies. I'll just skip ahead to the two length scale version of this. So imagine now you've got 2 length scales in your problem. Your 2-point correlation function has 2 maxima, 2 different length scales. You go through the same process, and what you might imagine, and we haven't done it yet, but this is just what we're expecting, is to find something that looks like the Swift-Herrenberg equation, but with 2 length scales in it. So it's q squared plus Laplacian all squared, and 1 plus Laplacian all squared, with a negative Laplacian in front. So that's just the linear part. And that is exactly the, with the exception of this negative Laplacian, which makes a big difference, that is the PDE that I was using as the model PDE in the first part of the talk. So just to compare, so I said I'd show you the Fourier transform of this this block of polymer system, and that's here. At least at the level of looking at Fourier transforms, it appears to have 2 length scales in it. I haven't approached the experimentalists to confirm this, but at least just taking the Fourier transform of this image, that's what you get. And this is the spatiotemporal chaos that I showed you. Now this is presumably not time dependent. This is frozen in, but nonetheless, it may be that similar considerations are coming in the polymer system. So where might you get your 2 length scales? The obvious thing is the core and the corona of your micelles, but there are other possibilities. It could just have to do with the different lengths of the blocks in your block of polymers. You've got different architectures, stars and dendrimers and all kinds of complicated things. And that would involve working not with the density of polymers, micelles, but with the density of the different components of the blocks of the polymer in a theory which I don't have time to really go into at this point. So just to conclude, what I hope is that ideas from pattern formation will be useful in understanding these soft matter quasicrystals, at least in possibly in other contexts, but at least in the context when there are 2 length scales. Making a quantitative connection could be done through this density functional theory phase field crystal approach, and that is based on expanding densities and around the reference states and gradients, and hoping that these things are not too big. The difference is not too big, and the gradient is not too big. So for near the liquid crystallization transition, it seems hopeful that it should work. One thing that will come out is computing these quadratic coefficients and using those to see to what extent they influence the behavior. That's it. This is all in 2D so far, but it can be done in 3D. Then, of course, I've been talking here about polymers and soft matter. A related question is, an obvious question to ask is, can any of this be transferred to, for example, some of the metallic quasicrystals that I showed in the very first slide? And there, the two-length scales could come from, for example, the different sizes of the atoms in the alloy. So thank you very much.
Thank you very much, Alastair. Question?
I think I saw in one of your phase diagrams two different regions of stability for the quasicrystal,
Yeah.
separated by a transition.
Is this the one? Or in the experimental phase?
Experimental one, I think. So the white regions, we went there. The white regions there are stable quasicrystals.
That's right. Yes.
So are those do those have this same space group?
Yes.
You know?
Yes. These are all 12-fold quasi patterns. This is
But
computing.
do they have the same mirrors and glide planes and?
I'd have to ask the experimentalist. In fact, I have asked the experimentalists to show me their data, and they say it's on a mag tape somewhere. And
Well, they don't have good enough data to see that. The experimentalists, I'm sure. Except maybe Bates.
so this is what they would be looking at. They're taking images of
Is that Forster's data? No, that's done. Oh, I see.
Dingenumbenher, the experimentalist here. So this is
I don't have big enough.
So when you do the theory,
yes.
do all the 12 points go up and down together, or are they sometimes out of phase?
They're sometimes out of phase. Yeah.
And the line between is from going up and down together to going out of phase, or?
Okay, so I can't say about the experiments because I don't have that information. What I can say is in this model, it's a simplified model, and we have thrown away the time-dependent forcing. So they don't go up and down in phase or out of phase because that has been discarded from this model. Okay, I have done other models where that is included, but the analysis is more complicated. These things, I wouldn't want to say that they're identical. They are all 12 amplitudes are non-zero, and the amplitudes are almost the same. And I've only looked at the amplitudes, not the phase relationships between the amplitudes, which will have a difference, which will make a difference to what they look like. Okay, so this has been simplified. This picture here has been simplified. So there's structure in here that I haven't shown you. Mm-hmm.
If you regard the Qs in some sense as the rate at which one energy is taken out of one mode and put into another, then would you expect the QWZ and the QZW to be the same?
Okay, so for problems that come from the variation of a free energy, there will be restrictions on these Qs, and it may well be that they are the same for those problems. For the Faraday wave problem, they're not the same, by no means, but that is not a variational problem.
Yes.
The soft matter community has a slightly different way of trying to understand these micellar quasicrystals, and I'm wondering how we can connect them.
Mm-hmm.
There's a pair potential for particles that was proposed a long time ago by Zugatov.
Mm-hmm.
And it has a single well and a bump. It's like a Leonard-Jones pair potential that favors local polytetrahedral ordering.
Okay.
And then it has a bump that is a repulsive interaction at the next neighbor shell that inhibits close packing. And so when the fluid is say cooled down or compressed, then it is unable to switch to an FCC packing, and you can get these Frank-Casper phases, one of which is this dodecagonal quasicrystal, or its sigma approximate. So then if you look at the micellar systems, they're squishy balls, right? And so we published a paper in PNAS about a year ago where we showed that if you just take a hard core with flexible corona, and you tune the flexibility of the corona, which is what you basically have in the black copolymer micelles and the dendron micelles, all these other ones. Then if the hard core if the corona is rigid, you just get FCC right away. And if they start to be more flexible, you get BCC, and then you get A15. And Randy Kamian and Zahral, they have a nice theory explaining why this is. It's basically trying to approximate the Ware-Phelan foam by maximizing the entropy of that corona. And we found that if you then just add a little bit of polydispersity, meaning not all the micelles are perfect spheres, but some of them, like 10, 20%, are a little bit oblong, you get the dodecagonal quasicrystal every time. So we went back to the experimentalists and asked them, what does your distribution of micelle shapes look like? It turns out that they always have this long tail with about 20% or so, 30% are actually not so spherical. And that's enough, I think, to keep you from close packing FCC.
Right, okay.
And give you this. So I'm wondering now how to connect that.
Okay, so one way of doing that would be through these. It would depend on how you treat these terms and these terms here. You can look at non-spherical particles if you treat this not as a function of just the distance separating the two particles, but also of their orientation, and that would that's in the pair potential, but that would show up in your 2-point, but probably also in your 3-point correlation function. 3-point correlation function is typically not included in the phase field crystal literature,
Right.
And it would have to be included, I think, to take that into account.
Interesting.
Brief, and maybe it's a question also for the audience if they're interested in density functional theory. So this shoulder that you described, I was basically looking at the flow evolution that you prescribed, the gradient flow structure, and it looks to me like it's potentially non-convex in the energy, so you may have a backward-forward parabolic type structure there. However, you've got also this 2-point correlation,
Yes.
and that's giving you a higher order regularization. So in fact, that actually might be useful to have that term in for the 2-state system.
Right. Okay.
In order to regularize a problem. And so the remark, if that's true, is that you showed these patterns which you said are presumably stationary. That was your last image.
The last image.
Yeah.
This
You said that these were presumably stationary.
in the polymer system. Well, it's probably annealing.
There
Right.
might be a slow dynamic
Yes.
associated with that, and that would be an interesting problem to look at
Yes.
from a limiting standpoint.
So my understanding is that they let this sit for 2 or 3 weeks before taking a picture. But 2 or 3 weeks is not necessarily that long on a polymer timescale.
It's evidence that it's evolving.
Is there evidence? I don't
No,
know.
it's evidence that it's evolving if they're waiting 2 or 3 weeks.
Okay, well, I think we should bring the proceedings to a close. Thank you very much, Alastair.